Welcome to Mode Concept. We are still on Introduction to Embedded Systems, a practical aspect of it. Having completed the Lab 1, 2, 3, we are going over to Lab 4. So, without much delays, let's start immediately. Don't mind that. This is Lab 4. Interfacing a transistor with a microcontroller unit. This is very, very important to us to know how to interface a transistor with a microcontroller unit. This is because most of the devices that are meant to be used with our microcontrollers are very powerful devices, in the sense that the current they draw from the port will always be higher than what the port will offer, which will in turn destroy the port. So to save this situation, we bring in a transistor. So this transistor just acts as a switch. It only takes a little current from the port to switch the device on. Just a little current from that port that might not power the device, just to switch on the transistor that will now in turn allow current from somewhere to power the device. By so doing, the device will now come up and our microcontroller unit will equally be intact and work well. So now, in this practical, our aim is to understand and get familiar with the interfacing of a transistor with a microcontroller unit. We shall be using NPN transistor. Not as if there is major difference between the way we use NPN and the way we use PNP. There is no major difference. It's just a matter of using the normal, any one that will do the work for you, you bring it in. So our requirement still remains the same, just that now we are bringing in transistor into the work. With transistor, we can use BC547 transistor. That's just that. This particular lab is similar to the lab 3 that we blinked many LEDs, but in that lab 3 we would not bring any transistor. We interface our LEDs directly, but now transistor has been put into place. That's just the difference. The program will still be the same. So as I said earlier, the port of microcontroller cannot deliver more than 20 milliamp. Meanwhile, some devices, some motors, requires more than 20 milliamp to run them. If you connect such motor to the PIC port, to the microcontroller port, it will not work. It will not run it. Rather, it might even destroy that port. So the only way to run such device is to bring in a transistor, take a little current from the port, switch on the transistor, which will now in turn allow major current to flow to supply to the device we are trying to run. So that is it. And when we bring a transistor into our lab 3, you will notice that the LEDs will glow better because they will now receive as much current as they desire. Though LEDs are not the target because LED doesn't require much current to power them. They are still within the limit of what the port can offer. So our major target here is those devices that require much current, much large currents, like our motors and so on. So this is our circuit diagram. As usual, this one now we brought in the transistor here. You see, when we take a little current from this man, we'll use this 1K to limit the current. Take a little current from this man, deliver it to the base of this transistor. It switches it on, allowing major current to flow from this supply here to ground, thereby giving this man whatever you interface here to whatever you connected here to receive the volume of current it requires from the source instead of sourcing for current from this place. So this is how it is. We brought in 7805 here. That is the normal thing, so that you can only collect only 5 volts to this PIC. So now our program is still the same with lab 3 program. We just want to introduce a small thing that will help our program, that will help us make our program simpler. So we just brought in sub procedure instead of using directly delay this, delay that, which will now make us to start having delay this, delay that all over the work. So whenever we want to change our time, we'll now start going through the whole work to affect the changes in the time. But when we bring in this sub procedure, if we want to change, make any change in the time, just go to the sub procedure, make our change, which will now affect wherever we have that weight inside our program code. So now this is sub procedure. We use the name wait, sub procedure wait. The delay 2.5 seconds. And so that's our wait one, wait two, 1000. So that this one will be when the device will be on, when the device will be off. Wait and wait one. So if not, all over the work will just become delay this, delay that, which will be so cumbersome. So now this is the main program. We say 3b equal to 0, meaning that we want all the bits of port B to be an output port. Port B equal to 0, meaning that we are initializing port B, making it digital, enabling it to be able to receive instruction. Then CMCon equal to 7, that is the comparator control. Then we go to our program proper, start port B dot 3 equal to 0. That is, let port B dot 3 remain 0. Port B dot 1 equal to 1. Then turn on whatever you have in port B dot 1. And delay is wait. This wait is delay for 2.5 seconds. Then we continue. After that 2.5 seconds, turn off whatever you have at port B dot 1 and turn on whatever you have in port B dot 2. And wait again for 1 second. Wait for 1 second. After 1 second, turn off port B dot 2. Whatever you have on port B dot 2, turn it off. While you're turning it off, turn on whatever you have in port B dot 3. Then wait. Let's wait for 2.5 seconds. After that, go to start. That's just the program. But before we start using this program, as we always say, we have to do our design. After our design, we now come to the program. That's just the way it is done. So we are going to go to Proteus now to start our design proper. So I will not just go through this procedure to start reading out this procedure. No, it's for you to follow. But for me, I have to go to Proteus and start doing the work so that you will follow me. Okay, my Proteus has opened. I'll go straight to schematic capture. This schematic capture, I will go to P to pick my component. I need PIC16f628A. I'll need min res 1k. What is it? I need LAB red. Green. Orange. I need transistors BC547. Then I'm going to okay. So that's it. I'm going to start my connections. That's my design. I'll drop my PIC. It's small, I'll zoom. Okay. I will hide the properties of this resistor, that my work will be neat. Okay, now I will get my transistor BC547. Okay, so I'll make my connection. This, this, that. So now this, this, that. I'll go to terminal mode, pick ground. This is common ground. Okay, pick my power, 5 volts power supply, or 9 volts as the case may be. Then there's something I'm missing. There will be a current limiting resistor here, and this is the only way our LED will be. So I'm going to correct something. Now. Delete this. Bring in my LED. Before that, LED red. Or hide the properties. Bring in orange. Hide the properties. Bring in green. Also hide the properties. Make my connection. My resistor, going to turn it the way I desired it. We'll make it 220 or 330. We'll make it 330. 330. Ooh. 330. Ooh. I'll zoom out a little. But that's the zoom in and choose different map. Go to terminal mode, cover power. So there is no need to pull up the master clear on Proteus here, but when we are doing it in real life, we'll pull up this master clear with 10K and take it through a reset button to ground and connect this man to power supply and ground. So So, but here, all the things are automatically done, both the oscillator, the pull up, and all those things. So, we'll put our program and run our simulation. So, let's see what happens. Let's go to MikroBASIC to run our program. To MikroBASIc. Okay, it's open. We'll just go to new project. Standard project next. Project name, call it CT225 LAB4. I want to save it where the other ones are. So that's it. So yeah, let's say okay. My oscillator, make it 10 mega. Let's see next. Finish. So because I have already written my program as I showed you, I'm not going to type it again here. I will only paste it and compile it and use it. So I'm going to go back to where I have it. It's in my program. It's my program. Just copy it. Control C. It's in two sections. Copy this first one. Control V. The next one. Control C. Control V. So now that is that. So I've explained this program before. I'm just going to run it. I'll save it. Run. So program has finished running successfully, and the hex file and the other files have been generated. I will now go to my design in Proteus. I'll click on the controller, go to program file. It's on the documents CT225 LAB4. So oscillator is 10 mega, we choose the program. So let's run the simulation and see what happens. See, our first LED is not coming up. You have to go and check why. You have to go and see why it's not coming up from our program. Port V.0. You see, the program we wrote did not really go well with the design, because the ports we chose in this design is not exactly what we chose in the program. That's what I was telling you earlier. Let's can see. Let's go to program here. We use ports B.0, B.1, and B.2. Let's go and check in the program. Here we used B.1, B.2, and B.3, which is not what we use there, so it's not going to give what we want. So we'll either change the program or change the design. So I'm going to change the program so that we'll have port B.2, port B.0, so let's save, build and run. Now go to design, let's check simulation. See, so you can see that is now okay. You see, that is how it is. That's why you are asked to do your design first. After doing your design, you can write your program based on this design. See, this error came because we wrote our program differently. I will now start to copy it after we have done our design. So always do your design and now write your program based on the design you have done. So for the sake of Proteus, if we want this LED to glow better, we reduce the current limiting resistor, reduce the value just for Proteus sake. But when we are doing it in real life, this 330 is okay because our calculation then gave us 300 ohm. You see, so let's just reduce what will happen to Proteus and see what happens. Let's make this one 220, 220. 220. 220. Let's see that. The LED is showing better regulation now because I reduced this current limiting resistor. So if you still reduce it more, it will blow more. So in some occasions we connect our motors on this side, and sometimes we connect our motors using relay, so that the relay, when the relay is triggered, it powers the motor. So that is just that. But the good thing is that this is how to interface a transistor, so the transistor will now help us to power whatever device we want to run, whether relay, motor, or whatever. So let's go back to the next thing we have on the lab, in our lab. So I'm going to show you something about this program we have written. Remember here we chose port B.3, port port B.2, not 3, port B.0, port B.0, port B.1, port B.0, port B.2, port B.1, port B.2. So as you have 0, 1, 2 of the port B's, you can still change this program. This program here, you can see how many lines we have in our own code. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines after start. You can still decide to reduce this code by bringing in our bit as byte. We no longer treat port B.2, we treat port B as a binary. Let's see what I mean. You see, port B as binary. So port B has 8 bits. So these are the 8 bits of port B. So when we want to refer to port B.0, port B.1. So for this one now we have port B.2 and port B.0. This one will have port B.0 as 1. Becomes port B.0 as 1. Port B.0 as 1. The rest 0. That's the only one that will come up at this time. Then wait for this length of time, 2.5 seconds. After it, turn on port B dot 1, port B dot 1, as we have it in the program. Port B dot 1, turn on port B dot 1, while other ones, while port B dot 0 remains off. So turn on port B dot 1, while port B dot 0 and the other ones remains off. Then wait briefly, as we have it in this wait 1. Then port B dot 2. See, port B dot 0, port B dot 1, port B dot 2 comes up, other ones remains off. Then wait again. After that, you go back. So now we have 1, 2, 3, 4, 5, 6, 7, just 7 lines of program. Most times when we have used this binary, it helps us to have small code, which we will now use our brain to do the work. Since it's binary and this will computer understands thread, it makes our program more simple. Port B dot 0 equal to 1. Port B dot 1 equal to 1. Port B dot 2 equal to 1. See, so that is that for this program. If you still run this program, it will still give us what we have gotten in our simulation. So this is that same simulation results. So the one I did before. Now we'll go back to the observation. What did they observe? They observed how we interfaced our transistors. But you only observed how the LEDs are connected here. And what I said, in most cases, when we don't want to connect a LED, we can connect a relay or connect a motor based on what we want to connect. So if you only observed how these LEDs we are blinking based on the program that we have written. So what precaution did you take? So for me, remember, because I did not type my code, because I did not do my design first before typing the code, I first of all write the code. So while I was doing my design did not tally well with my code, making my work to do something different from what I desired. So I have to go back and did the work again. So always do your design first before you write your program, as precaution. Then always interface your devices and components in the proper way, so they will give you what you want. So, and so many of the other precautions. So now, what is the conclusion? The conclusion could be that this same blinking of a LED and interfacing with the LED still work as the foundation to traffic light control design and other similar systems. So, and the transistors helps to save this port. So in your conclusion, you can still have it again that with the introduction of transistors, the ports are saved, so that thereby not allowing them to give more current than they can offer. They are saved. So anyhow you want to put up your conclusion, put your own and let them be in your own words. That's just the important thing. So that is the whole idea. So thank you for following this lab, and I believe you have gotten something reasonable. You have added knowledge to yourself. Do well to write your report very well if you need to. If you are not writing any report, pick up some, just play around with this design and play around with MikroBASIC to learn more. So do well to like this video and subscribe to the channel, so if you have not done that, so that you'll be following the labs as we are progressing. Bye.